Thanks very much. Thanks especially to the organizers for coordinating this workshop. And to tell the truth, I'm really a quantum thermodynamicist and a quantum information theorist. So I spent a lot of time with those communities, and it's really a pleasure to reconnect with this one. The title of this talk always happens when I'm just starting to start a talk. Clicker won't work. There we go. So this talk's title refers to Adam Brown and Lenny Susskind. I think I saw at least Lenny amongst the Zoom participants. Probably most people here know them. And I met their work probably later than most people here because, again, I really am a quantum thermodynamicist. But I met it through my PhD advisor, John Presko, who back in 2016 sent me an email saying, thermodynamics of complexity might be an interesting subject for you. He forwarded an early draft of this paper, which probably many people here know, Second Law of Quantum Complexity. So to tell the truth, I actually wasn't very interested because I had just come up with a bunch of questions of my own, and why would I want to answer other people's questions? But eventually I came around in the past 5 years because this paper lays out, or writes out, especially in the context, the broader context of literature in this community, a number of interesting conjectures that have become quite prominent. It was from this paper, moreover, that I learned about the concept of quantum complexity as it is thought about in this high energy theory community. So by quantum complexity here, I mean how difficult it is to implement some desired unitary on n qubits or other subsystems. For instance, in the absence of noise, in order to perform the identity operation, you don't have to do anything. So the identity operator has a complexity of 0, and the maximum possible complexity scales exponentially with the system size because of a counting argument. There are multiple ways of quantifying the complexity. One is attributable to Michael Nielsen. So Michael and collaborators imagine some quantum many-body system evolving under a fixed Hamiltonian, which will implement some unitary that changes in time. We can imagine this unitary is tracing out some path in the space of unitaries. We can attribute a metric to that space, and we can use differential geometry to calculate the distance of that unitary from the identity operator. Because of this differential geometry, I think this means of quantifying complexity is beloved to high energy theorists. There is also a means of quantifying complexity beloved to quantum information theorists. I'll call this the exact quantum circuit complexity. This is the least number of gates that you need to affect a desired unitary. These gates don't need to be geometrically local. The exact quantum circuit complexity upper bounds Nielsen's complexity, as we can see in this cartoon. The identity operator here is what we start off with. This unitary is some distance u away. Michael Nielsen's geometry involves this smooth red curve, and the exact quantum circuit complexity involves this jagged green line. Because of those jags, the exact quantum circuit complexity involves a longer path, so it is in the upper bound. And these jags are here to represent the discrete gates that we implement in this method. However, under an approximation scheme that I'll refer to later, the opposite ordering holds. Why do we talk about complexity in a workshop like this? Because of its usefulness in holography. So as probably everyone here knows better than I do, in ADS we can have two black holes that are connected by a wormhole whose length grows linearly in time for an exponentially long time. The dual of this in the CFT of this two black hole configuration is a certain state of the boundary theory. We can measure local observables and even out of time ordered correlators of this boundary theory, but those reach their equilibrium values much more quickly. So the question is, how do we have this important quantity in ADS, which grows in this way for an exponentially long time, whereas we don't seem to have a corresponding important quantity in the CFT that exhibits the same time scale? Proposed resolution has been the complexity equals volume conjecture. So the volume of the wormhole could be proportional to the complexity of the boundary state. And after that, other things were proposed to be proportional to the complexity of action, or recently I saw a paper, complexity equals almost anything. Adam and Lenny laid out in this paper some conjectures about the complexity. I'll focus on two. One is the answer to the question, Mary, quite contrary, how does the complexity grow if you implement a generic quantum evolution? So the conjecture is that the quantum complexity generically grows linearly in time for a time exponential in the system size. The other conjecture is that we can define a meaningful resource theory for uncomplexity. Let me break down that statement. First, let's start with uncomplexity. Just as we defined complexity for unitary operators, we can define complexity for states. A state's complexity is the difficulty of preparing the state from a simple tensor product. We can think of the uncomplexity as the maximum possible complexity minus the actual complexity. This uncomplexity is useful. For instance, in quantum computation, we like to feed into a quantum computer a tensor product of zeros. The computer will then use this tensor product as blank scrap paper on which to write calculations. So we could say that uncomplexity is a resource. There's a construct in quantum information theory called a resource theory, which is a simple information theoretic model for any situation in which the operations we can perform and the systems that we can access are constrained. For instance, if we are performing a quantum computation, then we can't actually access infinitely many qubits that are perfectly prepared in the zero state. So the resource theory framework is actually one of my home bases. I spend a lot of time working with resource theories for thermodynamics. The resource theories are useful because they can help us formalize operational tasks like the distillation of high quality entanglement from lower quality entanglement, and help us calculate the optimal efficiencies with which we can perform those tasks. So the conjecture is a resource theory for uncomplexity can be formulated. I've had the privilege and pleasure of working with some wonderful collaborators in order to prove these two conjectures. Jonas Haferkamp, Philippe Feist, and Teja Kothakonda are in Jens Eisert's group in Berlin, and Anthony Munson is in my group in Maryland. In the first paper, we proved the linear growth conjecture, and in the second paper, we define a resource theory for uncomplexity. Since we have quite limited time, I have focused just on the first paper so that we can go into some detail. First, why do we need a whole paper in order to prove that the complexity grows linearly for an exponentially long time? This task is difficult and has been approached for many years. So people have taken approaches such as the following. We could focus on short times and derive results there instead of exponentially long times. We can also focus on high dimensional subsystems rather than qubits. One popular mathematical toolkit is the toolkit of unitary T designs, which approximate the Haar measure. And sometimes people just assume that there are no collisions in an evolution. Here's what I mean by that. And here's really why it's quite difficult to lower bound the complexity. Suppose that we're modeling our evolution with a quantum circuit, then earlier gates can be canceled by later gates. And so the complexity can conceivably decrease. For instance, suppose that we're performing our quantum circuits, we perform a C0 gate to entangle the two bottom qubits. So our complexity increases from here to here. But right afterward, we can perform another C0 gate that cancels the first C0 gate. This is a collision, and it decreases the complexity back to what it used to be. We expect that collisions are very rare. So sometimes we just assume that they don't happen. It's difficult to prove that they don't happen, but it is worth trying to prove because we try to do things rigorously. So to present the proof that I can offer, let me set the stage. Again, we'll deal with a system of n qubits. For convenience, I'll assume that n is even. We will imagine these qubits undergoing a circuit of unitary gates that couple 2 qubits together. So they're chosen from the special unitary group SU4, and they're chosen randomly, loosely speaking, uniformly random. Again, these gates don't need to be local geometrically. And this circuit model, this model of random circuits, has been used to model chaotic evolutions because it leads to some behaviors that mimic behaviors of evolutions under chaotic Hamiltonians. I'll notate the z components of the spin like so that 0 represents the +1 eigenstate. And sometimes I'll notate tensor products like this. We introduce some terminology and along with it, a certain way of thinking. Let's say that an architecture, A, is a certain layout of gates, a fixed number of gates that I'll call R. One very common example of an architecture is the brickwork architecture. We have a gate coupling qubits 1 and 2, then a gate coupling qubits 3 and 4, and so on. In the next layer, we have a gate coupling qubits 2 and 3, then a gate coupling qubits 4 and 5, and so on. Not 4 and 5, I can't count, or yes, I can't count today, that's okay. But you can see the pattern. And then the connectivity pattern repeats in the later layers. If we take an architecture and we slot in particular gates, then we get a circuit. We can take a circuit and contract it along those lines in order to get a unitary in SU2 to the n. This contraction is performed by some map, FA, that depends on the architecture. Suppose that you take a circuit and you introduce 2 vertical lines, 2 cuts, then we'll say that the gates in between those cuts form a block. And a block can contain a backward light cone. Suppose that there is some qubit, T, that connects to each of the other qubits via some path that consists just of gates. For example, let's consider this bottom qubit. So it enters this gate, and so connects to this qubit via the gate, and that qubit enters this gate, and so connects to this qubit, and so on and so forth, until we get all the way up to qubit T. So this path might be unique to this second qubit, and the set of all of the gates in all of the paths forms what we call the backward light cone. So if a block contains a backward light cone, then in a sense, it's well connected. But here's the main result, loosely speaking, that under this type of random evolution, the complexity grows linearly for an exponentially long time. So let A denote any architecture that we can form by taking T blocks, each with at most L gates, and each with a backward light cone so that it's somewhat well connected. And let's concatenate these blocks to form the circuit. In one very simple example, let's suppose that every one of our blocks is a brickwork block. So this block contains at most L gates for some number L, and we could imagine taking T copies of this block in our simple example. Again, R denotes the total number of gates in the circuit. Suppose that we take this architecture, we slot in random gates, then perform our contraction, we implement a unitary U. For each such unitary, the complexity is at most, or at least, the total number of gates in the circuits over 9 times the maximum number of gates per block, minus the number of qubits over 3. And this bound holds for times up to those exponential in the system size. So this is the sort of result that we were looking for. The key is this scaling with R, the total number of gates, because the total number of gates is a measure of the total time that has passed, because we perform gates sequentially in time. This minus n over 3 term is not very important because, again, it's particularly difficult to prove this bound at exponentially long times. And at times exponential in the system size, this term over here is going to drown out this term over here.
I have a question. So for different copies of the block, they use the same unitary, right?
So we're thinking about a circuit that consists of blocks. The blocks don't all have to be the same as each other. Just in a very simple example, I said, let's imagine many copies of this brickwork block. And this whole circuit implements one unitary.
This is all with high probability over the gate choices, like 1 minus 1 over exponential?
It's with probability 1.
With probability 1. Okay, because it's from this continuous math. Okay.
The key idea behind this proof is an idea that we call the accessible dimension of the architecture. But once again, here's an example of an architecture. If we slot in gates and we apply our contraction map FA, then we get a unitary. Consider the set of all such unitaries that we can perform using this architecture, just slotting in different gates. That set of unitaries forms the image of our contraction map FA. And that set of unitaries I'll call holographic U of A. The accessible dimension, dA, of our architecture is a measure of the number of degrees of freedom that we need in order to describe this set locally. To be more rigorous about the definition, I need to review a little bit of algebraic geometry. So we're introducing here into the study of complexity, algebraic geometry, as well as differential topology. Again, some toolkits that have been very useful and very fruitful in the past have been Nielsen's geometry and unitary T-designs, but it turns out that we can achieve this goal of answering this long-standing question about linear growth for exponentially long times using these two different mathematical toolkits. So suppose that we have some set of equations. The set of solutions forms an algebraic set. An example relevant to us consists of the sets of R 2-qubit gates. This set forms the solutions to the set of equations that define the unitaries, and in particular, the special unitaries. Every algebraic set is a semi-algebraic set. Suppose that we have a set of not only equations, but also inequalities. The set of solutions to that is a semi-algebraic set. A useful statement in this context is the Tarski-Seidenberg principle. So suppose that we have some semi-algebraic set, and then we act on it with a polynomial map. The result also is a semi-algebraic set. In our problem, this input semi-algebraic set consists of the sets of R 2-qubit gates. This polynomial map is a contraction map. And the output is the set of all the unitaries that we can implement using our architecture. And our contraction map is a polynomial function because it multiplies matrix elements together, creating polynomials. It's also true that if you have any semi-algebraic set, then you can decompose it into a union of manifolds. Each manifold has some dimension, and the maximum dimension of any manifold in the set is the dimension of the semi-algebraic set. Here's the punchline. The accessible dimension of our architecture A is the dimension of this set of unitaries implementable with that architecture. That's quite a bit of background, kind of basic background within algebraic geometry. But again, the main point is that this accessible dimension measures the number of degrees of freedom we need to describe the set of implementable unitaries locally. We can use this notion of the accessible dimension. We can reason about it using algebraic geometry and differential topology, and then we can infer about complexity, which we really want to learn about. Here's a sketch of the proof. I will just talk about the top layer outline of the sketch, or of the proof. First, we lower bound the accessible dimension. This is the most difficult step. You can show that the accessible dimension is at least the number of blocks in the circuit. The key elements in the proof involve, again, algebraic geometry and differential topology. Also, we construct a particular Clifford circuit. So the Clifford gates are the gates that map the Pauli operators to Pauli operators within a phase. And let's say that a Pauli string, an n-qubit Pauli string, is a term that I'll use to mean a tensor product of n single qubit Pauli operators and single qubit identity operators. So it is a fact that if you take any non-trivial, not all identity, n-qubit Pauli string, P, then you can turn it via a Clifford circuit into a Pauli operator that acts non-trivially on just one of the qubits. We can make it a Z that acts on the final qubit. So we use that fact. Also the fact that the n-qubit Pauli operators form a basis for the space of n-qubit Hermitian operators. The number of non-trivial n-qubit Pauli operators is 4 to the n-1. That is why our bound holds for times up to 4 to the n-1 blocks. Having lower bounded the dimension, the accessible dimension, we then upper bound the accessible dimension. The accessible dimension is at most 9 times the total number of gates plus 3 times the number of qubits. This bound is less difficult to prove, but it still requires some thought that comes from a parameter counting argument. So let's take all these ingredients and put them together to start reasoning not only about the accessible dimension, but also about complexity. Let's review the theorem's assumptions since we saw the theorem a little while ago. Again, A is an architecture. We can form it by taking T blocks, each with at most L gates, and each with a backward light cone, and concatenating those blocks. So that the total number of gates R is at most the number of blocks times the maximum number of gates per block. This architecture can implement any unitary in a set U of A. Suppose that we randomly pluck a unitary U from this set. What is the probability that we can implement this unitary with a smaller circuit, with fewer gates, our prime gates? In other words, what is the probability that the complexity of this unitary is actually less than expected? So what's the probability that the complexity violates our lower bound? We'll show that that probability is 0 using those first 2 initial steps. So here is this conjectured lesser number of gates. And let me recast this R over L in terms of the number of blocks T. And we can solve for T and find that T is lower bounded by 9 times the lesser number of gates plus 3 times the number of qubits. We've already proved a lower bound on the accessible dimension. We can easily chain these 2 inequalities together to find that the accessible dimension is greater than 9 times the lesser number of gates plus 3 times the number of qubits. Now, consider any architecture of that lesser number of gates, R prime. Let's call this architecture A prime. It too has an accessible dimension, and this accessible dimension obeys the same upper bound that we proved in step 2. Now we can chain these 2 inequalities together to conclude that the accessible dimension of the smaller architecture is less than the accessible dimension of the larger architecture. This is an important inequality, so I'll rewrite it. We can prove that if this inequality holds, then the set of unitaries implementable with a smaller architecture forms a subset of unitaries implementable with a larger architecture. Furthermore, this subset is of measure 0. So, and we can prove this using the dimension theory of real algebraic sets. So if you randomly pluck unitary U from that set U of A, such that the architecture is sufficiently connected, then your probability of being able to implement that U with a smaller circuit is 0. And that's exactly what we wanted to prove. This result has a few implications. One is further evidence that complexity is the right quantity to use to resolve the wormhole growth paradox. So complexity, since it grows linearly for exponentially long times, can be the dual to the wormhole's length, or whatever other quantities grow linearly for an exponentially long time in ADS. We can also extend this result in a few useful ways. For instance, we can lower bound the exact state complexity. This proved useful in our resource theory for uncomplexity. The left side denotes our favorite pure n-qubit state. And let's say that C sub S sub psi is the least number of 2-qubit gates that we need to prepare this state from a simple tensor product. We can prepare this state psi from the simple tensor product using some unitary U. Suppose that this unitary obeys the assumptions in our theorem. Then the complexity of this state obeys the same lower bounds, also for an exponentially long time. But the form of this exponential differs from the form of the exponential in the unitary result because the set of states is parameterized differently than the set of unitaries. Again, this result proved useful in proving statements about the resource theory for uncomplexity. We can also randomize the architecture. So we can eliminate one of the assumptions from our theorem, namely eliminate the assumption that in every block of our circuit, there is a backward light cone at the cost of making the bound probabilistic, which is what you just asked about. So in a simple example, let's suppose that at each time step, we randomly choose 2 nearest neighbor qubits in order to couple together, in addition to choosing the gate randomly. For instance, we could randomly choose these 2 qubits to couple together, and then those 2 qubits, and then those, and so on. It turns out that with high probability, these gates naturally form backward light cones. So connected circuits are inherently common. And if the gates form backward light cones, then the complexity of the unitary implemented obeys a linear lower bound. Here's the mathematical form of the statements. I'm introducing a parameter alpha that I'll get to in just a moment. Over here, we have the lower bound on the complexity. And again, the key is this R here, which is basically a measure of time passing as our circuit runs. So the complexity of our unitary obeys this linear lower bound with a probability that is somewhat high. So it's 1 minus something or other. Now about this parameter alpha, so this is a whole family of bounds for different values of this parameter alpha. For example, suppose that alpha is relatively large, then this alpha here is close to 1. So this linear lower bound is not suppressed. It could be suppressed to closer towards 0, but we're not suppressing it if alpha is large. And the probability that the complexity is this high is relatively small, because if this alpha is large, then this denominator is small. So this whole fraction is large. So we're subtracting off something large from 1. So the probability is small, which is what you should expect in this relationship between the 2 sides of the inequality. And as you might guess from the form of the inequality, a key tool that we use to prove it is Chebyshev's inequality. Finally, we can lower bound to some extent the approximate circuit complexity, by which I mean the following. Suppose that we have some unitary that satisfies the assumptions of our theorem. Then we might try to approximate this unitary with a different unitary, U prime, implementable with a shorter circuit, a circuit that violates our lower bound. Then U prime is probably quite different from U in the following way. For all small parameters, delta, there exists some epsilon greater than 0, such that with a high probability, 1 minus delta, the Frobenius distance between these two unitaries is at least epsilon. And we could replace this Frobenius distance with any other sensible matrix norm. Unfortunately, this epsilon can be uncontrollably small. How come? Because we're imagining taking that, going back to our proof, which involved some smaller architecture A prime and the set of unitaries implementable with that architecture, U of A prime. Now we're saying, now consider all the unitaries that are just near, slightly away from U of A prime. So if you can reach any of those, it's as though you implemented it exactly, even though you're just approximating it. So all of those are sort of reachable if we use the architecture A prime. So we're imagining taking this set U of A prime and enlarging it slightly to all the unitaries that are close in some matrix norm. And so we're taking this set and expanding it in all directions in the space of unitaries. So the accessible dimension, unfortunately, will rise to its maximum possible value. And so that very important inequality, that step in our proof, dA prime less than dA, one accessible dimension less than the other, tends not to hold. So the accessible dimension might be just too crude a tool to use in order to lower bound the exact circuit or the approximate circuit complexity for exponentially long times. But that just leads to an opportunity for future work. So we could try to strengthen this lower bound on the approximate circuit complexity. There's a strategy suggested at the end of our paper. We could take this set of unitaries implementable with the actual architecture A, and take the set of unitaries implementable with a smaller architecture, U of A prime, and the expansion of it, and see in what way they overlap and try to prove some conjectures about that. And if we can accomplish that, lower bounding the approximate circuit complexity, then we can lower bound Nielsen's complexity. Because Nielsen's complexity upper bounds the approximate circuit complexity he showed with collaborators. And this approximate circuit complexity would be lower bounded with the desired bound from objective 1. Also, this accessible dimension has proved very useful in proving an outstanding question. So it's this new mathematical tool that we have in this context. And perhaps it could be useful in other problems, in holography or many-body physics more generally. Again, it is quite different from the mathematical tools that are usually used in the context of quantum complexity, of Nielsen's geometry and unitary T designs. So maybe it could have applications to Brownian circuits and hybrid circuits formed from random unitaries and projective measurements, or other problems. I'd be interested in hearing whether anyone has ideas about how it might be useful in holographic settings. Also, there's a whole set of opportunities related to the resource theory of uncomplexity, which I didn't have time to talk about. So in summary, quantum complexity is a useful topic to think about in holography, but also outside. It has applications to condensed matter, and as we saw earlier today, straight quantum computation and experiment. A couple of prominent conjectures about it were laid out in Adam and Lenny's paper and surrounding family of literature. First, we can conjecture, it is very reasonable to conjecture that quantum complexity grows linearly for a time exponential in the system size. And one can conjecture that we can define a resource theory for a lack of complexity. We presented proofs of these two conjectures, so I will admit my PhD supervisor was right. This was actually an interesting paper. Even if it took me about 4 years to come around to his point of view, I definitely agree. And we saw that algebraic geometry can prove a useful toolkit, especially as giving rise to the concept of the accessible dimension of a circuit architecture in this context. So, thank you for your time.
Your first theorem gave for probability 0 of a shortcut if you want to get a certain unitary exactly. Can you say anything about what happens if you're willing to make an error epsilon in constructing a given unitary?
So an approximate unitary rather than an exact implementation.
Yes.
After proving the theorem, I mentioned that there are some extensions, and one of them is to slightly robust, be nice to make it stronger. Lower bound on the approximate circuit complexity when we're considering being able to have some desired unitary and then approximate it with some shorter unitary. Then we see that if you use a shorter unitary under the assumptions of our theorem, or a unitary that is so short that it violates our bound, let's just say a shorter unitary, then the distance between those two unitaries implemented is probably quite large. And again, that is because of how the accessible dimension can change quite sharply when we expand the set of unitaries that are acceptable to implement. And so that's why we it is certainly an opportunity to lower bound the approximate circuit complexity still.
I'm surprised it can be proved with the same method because the low dimension set could be close to every point. So it seems that bounds on dimensions of the bounds on the accessible dimension wouldn't give the information where you allow the error epsilon.
So
You need to know something about the geometry of your low dimension set.
Right. And so that seems related to how the set U of A is related and sort of overlaps with the set U of A prime that you're actually implementing. And so if under one way that they could be arranged, then all of the unitaries in here could be rather far from all of the unitaries in here, but if they're sort of intertwined, then you could actually potentially approximate a circuit or a unitary U of A with just a circuit with architecture A, just with an architecture A prime. I'd be happy to talk about the conjectures related to how these are intertwined. We say a little bit in the back of our paper. We haven't figured out a way to prove these conjectures, so it would be.
Is there a useful notion of the degree of these semi-algebraic sets? Because what you roughly want to know is that the small set of smaller dimension isn't too complicated. And I was wondering if the degree of the semi-algebraic set is a useful concept.
Could be. I haven't thought about it.
For the resource theory of complexity that you mentioned a few times, one potential problem to me seems always that the maximally mixed state will be preserved under any class of operate, like a lot of reasonable classes of operations, and then the entropy or the neg entropy becomes a measure. So I was wondering how you get around that, and if you can say a little bit about the class of operations that you consider.
Yeah, it took us a little while to find a class of operations. For background, for people who aren't familiar with resource theories, a resource theory is defined by a set of free operations that we imagine that our agent can perform very easily for free. And so we were imagining that our agents can perform can choose any 2-qubit gates, but the gate that is implemented is randomly chosen from a little epsilon ball about the desired gate, so that there's always a little bit of uncertainty there.
Isn't the maximally mixed state preserved by that class of operations?
Yes.
So doesn't that mean that the entropy is a measure?
An entropy that tracks the complexity. That, to tell the truth, I've been focusing for so many weeks very hard on the linear growth paper that I need to sort of reset in terms of the resource theory paper. So let me get back to you afterward.
I have a simple question. How did you use the condition for the backwards Nicole in the proof? What role does it play? Yeah, can you explain a little more on that?
This might take a little while to rewind. It's in this step. When we lower bound the accessible dimension, we again can construct a Clifford circuit that takes an arbitrary n-qubit Pauli string to a Pauli string that operates non-trivially on just one qubit, which we can choose to be the last qubit. And we construct that circuit by using the connectivity of the backward light cone.
So another question, kind of keeping in this exact setting, is there any hope of using these sort of techniques to prove a lower bound where you're applying the same unitary U over and over, like you pick the same gates for each block as you repeat? Because then just kind of looking at this, it looks challenging. You might not be able to set each Pauli kind of separately per block.
Right. We do need in our proof that the number of parameters needed to describe the circuit keeps growing. So it wouldn't work if you just repeated the block with the same gates. I wasn't sure if you meant.
Yeah,
Okay,
with the same gates.
gates.
Yeah, because then that looks a little closer to, applying a fixed time-independent Hamiltonian.
Right.
Yeah.
Yeah. So no, this doesn't apply to a fixed time-independent Hamiltonian. It's more the random circuit model that in some ways reproduces results from the fixed independent Hamiltonian.
Great, thanks. Any further questions? Yeah.
Yeah, so in the K-design approach for the random circuit, it was kind of important to lower bound the gap of certain Hermitian Hamiltonian. Is there interpretation of your accessible dimension in terms of that quantity?
So you're asking if
Yeah, I'm basically asking
gap
the
in the
connection.
Hamiltonian is playing a role in this proof.
Yeah.
This is more about sets of unitaries. So first the set of gates drawn from, and the set of unitaries implemented. So not so much looking at the spectra of the Hamiltonians used to produce these gates.
Any further questions in person or online?
That's just a quick follow-up. So if you fix the block, like fix the time independent Hamiltonian, the linear growth probably will not be, right?
Our proof doesn't apply there.
Okay, but do you think is any what kind of improvement can we do for this fixed Hamiltonian?
So my understanding is that the classical analog of that problem of lower bounding the complexity for a fixed Hamiltonian involves calculating the complexity of a given Boolean function, which is about as hard as proving P equals NP. And our proof is not that powerful. So I'm not sure quite how to get to that level. This is more at the level of, again, saying random circuit reproduces a lot of the features of quantum chaos with Hamiltonians.
Yeah, even if you make some complexity assumptions, it's still one still can't prove a linear growth, right? The papers in there are kind of still proving that it has to be super polynomial at their Pauli time. Still a long way to go.
There was one question over there.
Yeah, so if I understood correctly, you were mentioning that in the introduction that if you have, instead of spins, you have some large on-site Hilbert space dimension, then you have other tools. So can you comment on that?
Yeah, there are previous results about that. I would have to go back into my literature folder, but I think it might have been Nick Hunter-Jones, Fernando Brandao, and that crowd.
So can you prove something more? Like, can you compute the accessible dimension in that context, or these are just different tools that you use in the use?
That is K-design approach.
We use qubits just because our proof does apply to them. You could extend our results to subsystems of different dimensions. Just some of the exact numbers would be different.
But can you do more with that or no?
So we can prove linear growth for exponentially long times for subsystems of arbitrary dimensionality, rather than just requiring a large dimension limit.
All right. So with that, let's thank the speaker.